Hi, my name is Akarsh Kumar and I'll be presenting our work on learning in context decision making with synthetic MDPs. This work was done in collaboration with Chris Liu, Louis Kirsch, and Philip Isola. All of the mainstream AI progress in vision and language require very large datasets of real data. This is increasingly true in RL with works like Gato, Adaptive Agent, MindDojo, and VPT. RL foundation models are being trained on hundreds of real games, human engineered simulation environments, or even real world robotic setups. Given the importance of data and environments to AI and RL, it is very important to study this and understand what properties make good and bad data. Recent work has shown that synthetic images are surprisingly good at training visual representations models. Even super simple noise generating processes like the image on the left here are surprisingly competitive with real image datasets. We asked the same question for RL. How far can we get with only simple noise-like environments? We create many different families of what we call synthetic MDPs. These range in diversity from Markov chains and bandit MDPs to discrete, multi-discrete, and continuous MDPs. Some of the simpler, lower dimensional environments are visualized here for you. Each family defines the state space, transition function, reward function, and observation function, and so on to construct the full MDP. For many environments, we utilize randomly initialized neural networks as the random function mapping, defining for example, the transition function. Additionally, within each family, we define several axes of variation along which we can vary properties of the environment. For example, we can vary the state dimension, initial state variance, transition stochasticity, transition complexity, reward sparsity, and 12 more similar properties which we deem to be fundamental to MDPs. For each family and variation, we sample 2048 random MDPs from that distribution. Then, with the help of JAX and its amazing VMAP, we efficiently train 2048 specialist PPO agents, which then collect an expert dataset, which is then used to train the generalist agent. To train the generalist in context agent, first we project all the observations and actions to a universal observation and action space with a fixed environment-specific projection matrices. Then we augment this data set with the random projections. Importantly, this random projection is the same across the context of the transformer, which induces in-context learning behavior. The transformer is then trained with standard next action prediction. At test time, this agent can be deployed to a new environment by giving it few expert examples as the prompt and having it predict a query action for a query observation. Now, let's move on to the results. We compare our synthetic MDPs to agents trained on real environment data. The Oracle Aug baseline is trained on the augmented test environment, giving a performance upper bound. The Gato Aug baseline is trained on all the other Mojoko environments except for the test environment and is the method that we are comparing against. All other bars are the best synthetic MDP variation for that MDP family. If we look at the bottom middle plot, we can see that overall, synthetic MDPs are extremely competitive with the Gato baseline, with one family even beating Gato in performance. Here, we plot the overall transfer performance versus the different axes of variation we defined. It seems that initial state variance, transition locality, and observation stochasticity are the most important aspects of synthetic MDPs. However, more seeds are needed to draw more definitive conclusions. To wrap up, it seems that training on synthetic MDPs can indeed match the performance of training on real MDPs. At least this is true for the setting of in-context imitation learning and measuring transfer to new environments. Additionally, synthetic MDPs are a perfect testbed for understanding data and environments because they are so simple and interpretable. They also provide for an easy way to scale up data collection. For these reasons, we believe that synthetic MDPs are a fertile research area worth pursuing. One future direction that we are actively pursuing is performing unsupervised environment design on these synthetic MDPs to push the limits further. Thank you for your time.